What up? Welcome to 2.2 polynomial functions. All right. Uh, so this right here is just your standard form of your polynomial function. Okay. I know it looks daunting, but all this really means is the n's that you see here is when it's just n. This coefficient matches up to this power. This coefficient matches up to this power. This coefficient matches up to this power. A polynomial could simply be f of x equals x, right? Or it could be x to the 8th minus x to the 7th plus 5x to the 6th, etc., etc. Okay? So that's why we write it when we're defining things in this form right here, because it's allowing us to say any given polynomial function. I do need to specify one or two little things here. N is non-negative. And n is also or a sub n rather is not 0. Okay, because I would make this part go to 0. Okay. So the main thing I want you to focus on as we continue. Well, first off, let me mention a sub 0 is just your constant, whatever constant is again. Maybe it's 0, maybe it's an actual number. I don't know. But anyway, the main thing we're going to be focusing on, along with the polynomial itself, is this right here. Okay. We call this the leading coefficient. Remember that for later, right? Leading coefficient. And then this right here, that n in particular is the highest power, okay? We write our polynomials highest power to lowest power, okay? We don't mix and match. We don't do that here, okay? But whatever that term is that your n value is your highest power. You're going to need that for later. Highest power, okay? We're going to need it. We're referring to this a lot in this video, okay? So keep that in mind. Here's an example of a graph that's a polynomial function. How do I know it's a polynomial function? Well, it's continuous, I hope. Also, notice its turns. They're smooth. Even though I did not draw it smooth, they're meant to be smooth, all right? So they're smooth turns, continuous, all things pointing to it being a polynomial. Here's where highest power and leading coefficient come into play. They can tell us how our polynomial is going to end if we just know a couple things about your highest power and leading coefficient. So let's say hypothetically your highest power is odd and your leading coefficient is positive. So what does that mean for us? Well, that tells us that the limit as x goes to negative infinity of f of x is negative infinity, and the limit as x goes to infinity of f of x is positive infinity. So it's going to end eventually going up, and then as we go to negative infinity, it's going to end going down. Okay, somewhere in between there. I just drew a random graph here to kind of illustrate that. What might help you remember this is if you think about your x cubed graph, what happens with your x cubed graph? It ends going positive infinity and starts going down to negative infinity. Okay, another way to think about it. When n is odd and a sub n is negative, limit as x goes to infinity of f of x goes to negative infinity, and limit as x goes to negative infinity of f of x goes to infinity. So they swap, they flip, okay? Could look something like this. Begins going all the way up, ends going down, okay? And then down below here is when two examples when we have n is even. When n is even and the leading coefficient is positive, just like your x squared graph, goes up and up, right? Up, up. Limit as x goes to negative infinity of f of x is going to infinity, and also the limit as x goes to infinity of f of x also goes to infinity. And then for when it, that shouldn't say that should say positive. I'll be fixing that. When n is even and a sub n is negative, it's going down, down. Okay. When limit goes to x goes to negative infinity of f of x, it's going to go down to negative infinity. When x approaches infinity of f of x, it's going to go down to negative infinity. All right, describe the end behavior of the graph of each polynomial function using limits. Explain your reasoning using the leading term test. So we have this function right here. We have a leading coefficient of 4 because that's what's in front of highest power, and the highest power is 5, so it's a degree 5. So what does that mean for this graph? It means that if you look at your table, degree 5, that's odd. And you have a leading coefficient of 4. That's a positive number. So I can say that when x goes to positive infinity of, well, in this case it's g of x. Let me fix that. Of g of x, it's going to be equal to, or it'll be approaching infinity. And when it's going towards negative infinity, it'll be going to negative infinity as well. Okay, because it's odd and it is positive. Okay, and let's go to the other one. So we have this h of x function right here. H of x is equal to negative 2x to the 6th plus 11x to the 4th plus 2x squared, degree 6, leading coefficient negative 2, the 6 there, that's highest power. What does that mean? So as the limit of x approaching negative infinity of h of x, what does it do? Well, it's a degree that's even and leading coefficient that's negative. So it's going to be going to negative infinity for both as x approaches negative infinity and positive infinity. It'll be going down to negative infinity for both. So for zeros and turning points of a polynomial function, if we have a polynomial function of degree n greater than 1, it has at most n distinct row zeros, and at most n minus 1 turning points. Probably the most basic one, well, maybe not the most basic, but one of them, just so that it helps illustrate for you. Here's some random x cubed graph. How many zeros do we have? 1, 2, 3. Now, turning points, what do I mean by turning points? When we switch from positive to negative, right? When we switch from, in better words, from increasing to decreasing or vice versa. So that would be, use a different color. A turning point would be right there and right there. Those are your two turning points, right? Because they're switching from increasing or decreasing in one way, okay? Yes, you still have to remember how to factor. Haha. So, state the number of possible real zeros and turning points and determine all of the real zeros by factoring. So, possible real zeros. Possible reals. Highest power is 3, so that's a 3. And turning points, possible turning points, is 2, because it's n minus 1, and that's 2. So, we need a factor. What should you do every time to try to do? Find the GCF. GCF of these three terms is x. And the factors of negative 27 to add up to negative 6 is negative 9 and 3. So x minus 9, x plus 3. Set them all equal to 0, you're going to get x equals 0, 9, and negative 3. So those are your three zeros. Next example, we got f of x is equal to x to the 4th minus 8x squared plus 15. Let's solve. So with this one, anytime we have a power 2 and a power 4, I don't know if you've seen this, but you can make the first terms x squared potentially if we can do the same process, the factors of 15 that add up to negative 8. We got minus 3 and minus 5. Set them both equal to 0. We get x squared is equal to 5, square root. We get x is equal to plus or minus root 5. and then we have x squared is equal to 3. Square root, we get x is equal to plus or minus root 3. I forgot to mention possible real zeros. We have 4. Turning points, 3. Because 4 minus 1 is 3. Last example, and we will be graphing this. Possible zeros. Zeros is 5. Turning points possibly are 1 less than that, so it's 4. So let's factor. What you always do to you're factoring GCF. 3x to the third minus, or excuse me, not minus, 3x to the third factored out. Then we get what's left in the parentheses is x squared minus 6x, not squared, 6x plus 9x. No, just 9. No, I'm sorry, wait. I was right the first time. X. Oh, wait, yeah. X squared, x. Oh, wait, no, never mind. I don't know what I'm saying. I took out x cubed, not x squared. I kept thinking I'm taking out x squared. But anyways, that's right. And then we got factors of 9 out to negative 6. That's minus 3 and minus 3. Send them all equal to 0. And it would appear we only have 2 zeros, right? We have 0, because we set this equal to 0, and you get 0. And then we have 3 as well. So, and this is 0, since it's a power of 3, it occurs 3 times. In this 0, because we have x minus 3 times x minus 3, it occurs twice. Now, what does that mean for us? Well, when we graph it, we have zeros of 0 and 3. We'll call that 0 and 3, okay? I'm not looking for artistic perfection here. So it's going to end like that, and it's going to go down because we have a positive as leading coefficient and an odd as a highest power. Okay? Now, how does the fact that we at 0 occurs 3 times? So whenever we go through the point x equal to 0, it's going to look kind of like an x cubed graph, how it kind of just goes shooting up and then does a quick turn and goes back up again. So it's going to look like your typical x cubed graph. And then when it's coming back down, I'm not going to finish it yet. I'm going to talk and say that x equal to 3 occurs 2 times. So it's going to look like your quadratic when it hits it. Well, that's a rough drawing. Let's try it again. So it's going to look like an x squared graph, a little parabola, right at 0. Okay? That's a very poor drawing of what this function is potentially looking like, but you get the point because of where the zeros are and how many times they occur at that 0 and what you should do when it occurs more than once. Thank you for watching, and we'll see you in class. Bye-bye now.